Hi everyone, I'm David Millington, the C++ project manager at Embarcadero, and today I'm going to give a talk on smart pointers in C++. That's both what are they, and also more importantly, how do you use them effectively? How do you choose which to use, and what are the best ways in which to put them and use them in your code? I'm going to start off with the reason for using smart pointers, and it all comes back down to memory management. This is an old problem. You have a resource and you need to at some point delete it. So the example is a file handle or network socket. One example that I've used elsewhere is a tap. If you turn a tap on, you want to guarantee that at some point you turn it off again, otherwise you're going to flood your house. And so if you are writing code that deals with a tap, you want to use a coding technique that guarantees that no matter what, no matter what exceptions, no matter what code flow, that tap is going to get turned off. So that's an example of a resource or something where something needs to happen and you need a guarantee. And of course, the most common example of a resource is a pointer, memory or objects or any heap allocation, and this is where smart pointers come in. The problem with manual memory allocation, with manual creation and manual deletion, is a risk of leaks. You need to make sure that you delete everything that you knew. And there's a habit in many programmers that they write the new keyword and they go and write delete immediately before filling in the rest of the code. Whether that's in a method or in a class that owns a pointer or something like that. And of course, if you forget to do that, that can be a problem. The other problem with having a manual pointer is that you need to track when it should be alive, what's using it, and if a pointer that you have is still valid. So if you have a pointer and it has an address, it looks valid as is pointing into memory, but how do you know that something else hasn't actually deleted it and you have an invalid pointer? And so these questions and also the manual tracking of deletion, such as always matching a delete to a new, are quite complex. And they become more complex when dealing with issues of ownership, of what owns a pointer, and they do not scale. And this, I think, is where it becomes really, really important. Ultimately, these are fundamental issues that can lead to problems in your code and that you have to get right. And manually doing this just isn't reliable. So to diverge to something a little bit philosophical, what is good code? Well, there's a joke that actually contains an awful lot of truth, which is that the only program that doesn't have any bugs is a program that you don't write. And to a certain extent, this is quite true. Code that you don't write probably doesn't have bugs in it, which you can extend to saying something like code that's using a well-tested standard library so that you don't re-implement yourself. Is far more likely to not have bugs. But I think more important than that is the issue of code complexity. So code that you don't write could be taken to mean that you should write very concise and very small code, and that's not a good idea because many people can write very short code, but it can be very complex and very hard to understand. And ultimately that's not a good idea. So code should be as small, as simple as it needs to be, but no smaller. But good code is also code that you don't have to think about. Code that is designed in a way such that it has a guarantee of correctness. And so applying that to resource management, where a resource is a pointer, good code there is pointer management that you don't write, pointer management that you don't have to think about, and pointer management that you know is correct and guaranteed to be safe. And that's where smart pointers come in. So I'm going to go back to some very basic C++ here, which is just to quickly examine scope and discuss when objects are destructed. And if you have a stack allocated object, it is destructed when it goes out of scope. So you can see in the code sample on the left, my class A is created inside the block defined by the curly braces. A is destroyed when it goes outside the scope in which it was declared, which is that last final curly brace. And similarly, when you have a class, a member variable is destroyed when the object that it's part of is destructed. So the code sample on the right uses new and delete, which is bad code that we're going to replace later on. But you can see that when you call delete foo, the member variable mbar that is part of the foo object instance is destroyed. So that's important because it leads to using ownership through RAII, resource acquisition as initialization, which is an object that is given and owns a resource when it's created, when it's initialized, and it can delete it when it is destroyed. So the code example on the left shows allocating a new array, and then immediately after an exception occurs. And so that array, the pointer np, is never deleted, it's a memory leak. Now suppose with the code sample on the right, you have a little class that is initialized, it's constructed with a pointer to an array, and its destructor always deletes the pointer that it was constructed with. Just calling that a smart pointer on screen. So in that code sample, the smart pointer A, even when an exception is thrown, is always going to be destructed as the stack unwinds. And so that means that even when an exception is thrown, the array will be deleted. And that's guaranteed. That behavior is guaranteed by the C++ standard. So this is safe behavior, and it's guaranteed behavior. And so a smart pointer is an object that takes a pointer and does something. It doesn't always have to delete it, but does something with the pointer when it's destroyed. And it's what it does that's interesting. So it could delete it, that's very simple, or it could keep a reference count and delete when that falls to 0, and we're going to look at examples of both of these in just a second. So C++ has had various types of smart pointer for a while. There was one called auto pointer back in C++ 98, and then the Boost standard library had a couple. In fact, shared pointer that you can see on screen comes almost exactly from the Boost implementation. But we're going to discuss the two ones that are in the standard for C++ 11, and that's stood unique pointer and stood shared pointer. Now, stood unique pointer is the one that I'm going to talk about quite a lot, actually, because it is the best of those two in most situations. It keeps a single owner of a pointer, so one pointer cannot be owned by two unique pointer instances. And it deletes when it goes out of scope, or rather when the unique pointer instance is destructed itself. So it takes a pointer, and then when the unique pointer instance is destructed, it deletes the pointer as given. Stood shared pointer is more interesting. It's for multiple users of one pointer or one object, and it keeps a reference count when given a pointer. And reference is a count of the users of a pointer, or the number of references to that pointer, which is slightly confusing terminology. It's not a C++ ampersand syntax reference. It's talking about the number of objects that have an interest or a reference to that pointer. So it increments the ref count when it acquires a pointer, and it decrements the ref count when it is destructed. But if it is the last reference, so the ref count goes from 1 to 0, then it deletes the pointer that is given. And it is the most often unnecessarily used type of smart pointer. Smart pointers should always be used in your code. You should, if you can possibly avoid it, never use a raw pointer. But I've seen a lot of code that used a shared pointer when a unique pointer would have been better. And I'll actually discuss this in a couple of minutes. But before going on, it's worth noting that both objects use pointer semantics, so they define operator arrow and asterisk. So you can use them in code just like a plain pointer. So quite often they're just a drop-in replacement. And if you are using raw pointers in your code and you want to improve your code quality by moving to smart pointers, which I strongly recommend, and which this entire presentation is trying to sell to you, in many cases you'll find they are a drop-in replacement. You won't have to change a great deal of your code So first of all, let's look at shared pointer. It's a very interesting kind of smart pointer, despite being the one that I said should probably be used the least. It's definitely the easiest to use. So shared pointer keeps a reference count, and the last shared pointer to destruct for a specific pointer deletes that pointer. So when the reference count goes to 0, it is deleted. That's very good for uncertain ownership. And I want to pause here to say that that probably indicates bad design. And it's also good for specific rare scenarios. One that comes to mind is when you have multiple threads and you want to have them act on some data. You have some constant data. Obviously, when you have multiple threads all accessing the one object, you don't want them to mutate the state, or at least you want to do so in a thread-safe manner. So let's assume you have a constant bit of data and you want to give it to some threads to do some work, and then you just want that bit of data to be deleted when the last thread that was doing something is finished. So a shared pointer might be one way to do that, for example. But in general, using a shared pointer indicates that you are not certain of the ownership of the resource of the pointer. And that probably indicates architectural issues in your application. In the code snippet shown on the screen, you can see two shared pointers, and they both refer to the same pointer. So the pointer that A holds and the pointer that B holds are the same thing. And when will the foo instance be destroyed? When whichever of the last of A and B are destroyed. And it's worth noting that the reference counting itself is thread safe. That uses it's atomic. But the deletion itself would occur in whichever thread it is that happens to have the ref count go to 0. There are a couple of other problems with shared pointer as well. I mean, first of all, it is easy. It's very easy to use because you can throw your pointers into a shared pointer, and you know that at some point it's going to get deleted, just because the last reference to it will delete it, and that means that as long as you have a shared pointer, the object is kept alive. As I said, that probably indicates or may indicate architectural issues in your application. There are a couple of other problems with that. The first is a reference loop. So A owns B, which owns C, which owns A, and no ref count there will ever drop to 0. And the second, which is important in language like C++, which is often very optimization focused, is that as well as the ref count being an atomic operation, which is useful for thread safety, as I mentioned before, atomic operations are a bit slower than normal, and the reference count is kept externally as well. Obviously, you can't add the reference count to the actual object or pointer itself. And that means that using shared pointer can be slower. So in my experience, you see it a lot in code bases that are new to smart pointers. And that's good because you're using smart pointers and you want to take advantage of using smart pointers, and you want to get rid of all the disadvantages or all the problems that we discussed earlier that come with using raw pointers. But it can indicate bad design. And it is better in that case to be aware of object ownership, to be aware of the responsibility for where a resource or a pointer should be deleted. And if you're aware of that, if you can track that in your code, then you should use unique pointer instead in almost all situations. So that brings us to unique pointer, which, as you can tell, is the one that I'm heavily promoting in this talk. So unique pointer is a single owner of a pointer. So that's where the unique name comes from, and it cannot be copied or assigned. It is very fast. So shared pointer, of course, keeps the reference count, whereas a unique pointer compiles down to exactly the same as using a raw pointer. There is no overhead compared to using a plain pointer. And it is also the simplest. It deletes when the smart pointer is destructed. And so you can see the code example there. It is the perfect example of RAII. The unique pointer A there is given a new foo, and when it goes out of scope, that foo instance will be deleted. And the same when it's a member of an object, such as when a class, or rather an object instance of a class, owns a resource. It's very simple and very straightforward. The only complex part comes from the question of not being able to copy or assign. So how do you move it around? And I want to point out here that not being able to copy or assign here is used to enforce that only one unique pointer instance can refer to a pointer, and also to handle the issue of moving ownership between unique pointers by making that explicit. So for those of you who remember auto pointer, which was an old smart pointer from C++ 98 days, that one was a bit dangerous and sometimes gave behavior that was unexpected, because moving a pointer was done using copy semantics. Whereas here you can see the unique pointer won't compile using the copy constructor. So how do you handle that? Well, you handle that in C++ 11 using move semantics, such as std move, as in the code sample at the bottom. And so in that code sample, unique pointer foo b equals std move a will move the ownership of the pointer held in A to B, and then A will then have null pointer inside it. There's a very common pattern where you have a method that creates a resource that creates and returns an object, and then later you want to give that to something. So I have some very much demo code on screen showing something that gets a resource and returns a foo object, and then later a method that takes that resource. And so again, the problem with the syntax is how do you deal with this very common pattern? And so the code snippet at the bottom shows that. So you can have a unique pointer of foo and get the resource. But if you pass that directly to the method taking the std unique pointer, you'll have a compile error. Instead, what you want to do is use std move, and that will compile and work okay. And also, and this is the important point, give the expected behavior for which of the unique pointer instances that are moving around actually owns the pointer. And so unique pointer works with STL collections as well, and there'll be a lightning talk on that later. So one thing that you might be wondering if you use smart pointers is, how do you pass them around in code? I mean, suppose you have code that used to use raw pointers and you pass around a foo pointer everywhere. So the code on the left used to, the method A used to have foo pointer f equals new foo and then later delete f. And you're replacing that with a unique pointer because you want the unique pointer's guarantees and safety. But you have the other methods that you want to call with the pointers. You have B and C, which used to take a foo pointer, a plain raw foo pointer. So what do? How do you pass them around in code? One of the most useful things here to realize is that usage indicates purpose. So in the code sample on the left, the unique pointer has a get method which gives you direct access to the pointer that it's holding. And if you are not certain that the unique pointer instance will actually hold a pointer, you might have null pointer or it might have a pointer, then you would want to pass you would want the parameter of methods B and C to be a foo pointer. And those methods, when they get a pointer, as you would expect, would check if that pointer is valid. And this is an example of usage indicating purpose. When you pass a raw pointer around, it is something that you need to verify. There is no guarantee. But of course, if you do have a guarantee, if you know that the object exists and you're just using a pointer because it happens to be heap allocated, that's when you use a reference. And so in the code sample on the right, you would just dereference f exactly the same way you would a normal pointer. Then so methods B and C would take a foo reference instead. Now, the third option that you could do is pass around the unique pointer itself, and of course, given the copy semantics and that kind of thing, you'd have to pass a reference to that. And the question is, why would you do that? Well, the only reason that you would pass a unique pointer parameter would be if somewhere in your code something needs to make use of not the pointer, but the unique pointer itself. And the only reason for that would be to change ownership. So you can see here that the usage indicates purpose, that passing a unique pointer would imply that the unique pointer itself is passed for a reason. And so you would normally use a pointer, or even better, a reference, unless that's deliberate. And the use of those indicates what the methods can expect. It indicates the validity and the existence of the object. And importantly, when you've moved your code to using smart pointers completely, and you never do any manual deletion, getting a pointer also indicates that it's not transferal, such as foo pointer f in one of these methods, also indicates that it's not transferal of ownership. So your code will know when it gets a pointer that something else is managing and looking after the lifetime of that pointer. So, what do you need to know here? Well, first of all, use smart pointers. They're very useful. You can use them almost exactly in most cases as a drop-in replacement of raw pointers, and they give you a great amount of safety in your code. You can access them by hash including memory. And a quick summary: unique pointer just replaces plain pointers and has smooth semantics, and a shared pointer is ref counter. It's useful and it's easy, but it is overused. And what I can recommend if you find yourself using a shared pointer is, this doesn't necessarily indicate something wrong, but just to pause and question whether you really need to use it. I was thinking when I was preparing this presentation about when I last used a shared pointer, and in the past year or so, I don't recall actually using a shared pointer in any real-world code that wasn't for a demo at all. There are situations in which I would use it, but they are rare. And thinking back even further to many years ago, I have worked on a code base that uses shared pointers extensively. And my feeling, for example, is that that is an example of a code base that uses them in some places where unique pointer would be better. There's also a really useful pair of methods called makeUnique and makeShared, and they construct an object of the type they're templates, so they construct an object of the type that they are instantiated with and pass their parameters. Through a quirk of the C++ standard definition, C++ 11 includes makeShared but not makeUnique, but you can find source code for that on the net. It's a few lines long, so just drop that into a utility header somewhere and use makeUnique. That means also that you never use new. So good modern C++ never uses delete. But in the code samples that I gave before, and I did this simply for simplicity to make it easy to follow what was happening, I used new. But best practice actually is to use makeUnique and makeShared. And so that will give you safe and reliable, clear ownership with non-leaking code. And I just want to re-emphasize that modern C++, well-designed, good modern C++ code bases never use delete. There is no sort of manual memory management at all. So I have some very useful links here. Some about unique pointer with an intro and some more information, and a code example of makeUnique, so you can take that and use it in your code. And also shared pointers. So the top link there on Stack Overflow explores the differences between unique pointer and shared pointer. And the second article expands on the dangers of using shared pointer. Now I'm also 4/5 of the way through writing a blog series at the moment that is writing a real-world application in C++ Builder. And of course, it uses smart pointers, and it uses unique pointer, not shared pointer. And that blog series is in the last link. So what I'm actually going to do is to now go over to show you that application just as a quick example of using a unique pointer in practice. Then after that, we'll come back and I'll put the site up with links and go to the Q&A. So this project is a quite simple but still real-world application that I was developing for the blog series that I mentioned in the previous slide. And it is a calculator, such as the kind of calculator you might find in the App Store on iOS or Android. It is running on Windows. You just type 52 times 3 equals, and it will give you the answer. A few other sort of neat things in there as well. So the form, obviously, in a well-designed application won't actually do all the calculations. There's a little calculator object, and you can see this mcalc, that's the thing that does all the work. And if we flip over to the form header and scroll, you can see that mcalc is a unique pointer. So iCalculator here is an interface. Another thing with good design is to try to separate the interface from the implementation. The form actually doesn't know about the tCalculator object that does all the work. It just knows about iCalculator, which I'll just control click on that, and here you can see that class iCalculator here. There are a few interfaces. The form implements the display interface, and the calculator implements the iCalculator interface. C++ doesn't have interfaces as a first-class language feature. They're really just pure virtual classes. However, the interesting thing comes when the form initializes that variable through create calculator. Create calculator here returns a stored unique pointer, which it does through use of make unique and the concrete implementation class tCalculator. And you can see here the 5-line template make unique that is missing from the C++ 11 standard. So you have to supply it yourself from the Stack Overflow link that was in the previous slide. So what this means is that the form here in its constructor has the mcalc object, which is created on the heap. And you'll notice that, first of all, new wasn't called because make unique instead of new. Second, that the form has no destructor defined because it doesn't need one, because this unique pointer will delete the calculator when the form is destroyed. So this, of course, is a very simple use of a unique pointer. As you can see, you can just access it using pointer semantics. So you use the arrow operator, for example, mcalc arrow set operator. So in terms of actual usage, it is exactly the same as using a raw pointer. Now for a slightly more complex example, we can flip over to the calculator itself. And the calculator has a number of operators. So operators are the things that implement plus or minus or multiply or divide. And I've implemented those as separate classes. So you have a multiplication class. And again, through an interface, you just say, go and do something with a left and right operand, and it happens that the multiply one multiplies and the add one adds. And this too is a unique pointer mop. However, the usage here is a bit more complex in the calculator because the operator is going to change a lot. I mean, you might press plus and then might press minus, and then when you press equals, you want to clear everything and that kind of thing. So let's go over and have a look and see what happens with mop. First of all, it's initialized, and instead of giving it a value, it just says empty brackets, and that means that the smart pointer will initially hold null pointer, so it won't have a value. Reset here is a useful method that will delete the pointer that it's holding and then set it to null pointer again. So there's no guarantee that a unique pointer has to have a value. You can have null pointer if you want to. You can see here I'm calling reset again, but this time I'm giving it a new operator. And so that too will delete the pointer that mmop is holding and then acquire the new pointer. And finally, some very interesting syntax here. Of course, when you have normal raw pointer, you can put it into an if statement, you can evaluate that through Boolean, and you can write exactly the same thing for a smart operator. Sorry, a smart pointer. So you can just go if mmop, which effectively means is the pointer held inside the smart pointer not null. And so, as you can see, in normal use, you would actually just highlights normal use. You can see I'm calling it here, mmop arrow calc. With normal use, you use it exactly like a raw pointer, including in if statements, and including with the arrow and dereference asterisk operators. And plus you get all the benefits. You have the safety. This code never has to worry about actually deleting an operator, because when the calculator object itself is destroyed, any operator that is sitting in mmop will be deleted. Plus you can do a few other cool things, such as reset it to nothing, or reset it to delete what it's holding and then give it a new pointer. So this is a fairly simple app, but quite a nice one. It's real world enough that it copies some applications that you do see on the App Store, and I think is a good example of using smart pointers. The series is called Learning to Program with C++ Builder. Perhaps a bit of a misnomer, since it actually assumes you already know how to program, but it's an introduction to C++, learning to program with C++, or with C++ Builder. And back to the links, and now we'll open for Q&A.